This year is quite special for one reason only. Usually we try and take the Jennings lecture around the country, and this year we decided to bring everyone else together for a conference and bring the Jennings lecture only to one location. And I think it's the first time we had so many people for a Jennings lecture, I would say, in a very, very long time. So it's going to be quite special for Helmut. I have to read. Last night I quickly typed into ChatGPT, since it's the way to go now. Who is Helmut? And funny enough, most of the information comes from our current website. So either ChatGPT is aware that we are hosting a conference, or maybe we have the best collective of information for him specifically. So maybe your CV you can just update on our website, and we can use that as a platform for yourself as well. And we actually are broadcasting this as well, only the Jennings lecture for those that can't be at the conference. But without further ado, I'm going to just quickly scan through a few of Helmut's accomplishments. Every time we do this, you sort of get humbled very quickly when you see someone's CV. So Helmut started off his PhD University of Wales. He then moved on and he joined the Institute of Soil Mechanics and Foundation Engineering and Computational Geotechnics at Graz University of Technology. And he's been there for 25 years. He's retired now, still very active. I think retirement is a misnomer in many aspects. I see Peter laughing. And it just never stops. I'm sure Helmut will be, with us. And he's obviously the chair of the upcoming 21st International Conference as well. So he's very active still. His research is basically allowed him to publish more than 350 international journal articles, which is quite an achievement. He serves on a number of editorial boards, and in 2005 he received the Excellent Contributions Award, a regional award from the International Association of Computer Methods and Advances in Geomechanics. That's a mouthful. And then he received the Best Paper Award of the Japanese Geotechnical Society in 2010, the George Stevenson Medal from the ICE. He delivered, the Sheshi lecture as well as the Sukle lecture in 2018, and he's still currently the president of the Austrian Geotechnical Society. And I think with that mouthful, I'm going to hand over to Helmut and say thank you very much for accepting as the Jennings lecturer. So.
Thank you. First of all, I thank Seiji for inviting me to give this very prestigious lecture. I'm very honored to be here. I think, and also for your hospitality. We had a couple of wonderful days organized by Peter and Tinky Day, so thank you very much for that. We enjoyed it very much being here in your beautiful country. Now, I think my goal today is to promote numerical methods, and I hope I managed to do that. But before I start, I want to acknowledge the work of my colleagues, students, co-workers, because at my age, you don't work hard anymore. You just present the work of others, and that's what I'm going to do. Now, I start probably a little bit controversial by saying these days everybody uses numerical methods. But is it done because your client asks you, please provide a few nice, colorful pictures? Or do you really do it to get a better understanding of your problem? Now, I can see that there's still a bit of skepticism about the usefulness of numerical modeling amongst practitioners. Some people say, well, we don't have the parameters, etc., etc. There is skepticism about it. But the goal of this presentation is to show you that numerical models can provide useful insight into practical problems. And that's why I keep most of it on showing you what we can do in practice, although I will give a bit of an introduction. Now, I tried to link this to Professor Jennings, and I found this quote. When he was professor at the university, he insisted, obviously, that he's still involved in practical problems. And I think that ties up, or at least I try to tie up this with my lecture, because I'm also at the university, but we try to keep in contact with the so-called real world and provide solutions for them based on the research and teaching we do. Now, the outline of the lecture will be, I give a short introduction. I make a little bit of a note on constitutive models and parameters, because that is still something which causes some issue at some stages. But at the end, I will concentrate on these 4 examples: an anchor load test, a slow-moving landslide. I on purpose call it slow-moving, because in Austria, we sometimes tend to call everything we don't understand creep. But it's not only creep, it's much more to it, okay? I had a lot of discussion on that in the institute sometimes. Then I do a bit on a compenetration test, and finally I finish off with an analysis of slope failure, again showing that numerical methods can do better than conventional methods. And then I come up with some final remarks. Now, if you look at pros and cons of numerical modeling, the advantages are clearly you can simulate the complete construction history. Well, at least approximately. I usually tell the students, or if we give courses for engineering companies, that they say, well, if you are the one responsible for the analysis, if by any chance you have a chance to go on the site, then please go on the site. It looks slightly different than on the computer, okay? But at least approximately we can do everything. The nice thing is we can do the interaction with water rigorously. That is something which is a big advantage. And of course, you can do drained analysis, undrained, consolidation, etc. This is not a big issue anymore today. Okay, it was some time ago, but now all the codes available commercially can do that. You can model almost any geometry. I will show you just a few slides in a few minutes. So there's almost no restriction on the geometry. If you have advanced soil models, they will capture important features of soil behavior. No model is perfect. I come back to that also in a minute. And you can take into account soil structure interaction, which is also very, very important. So all these things you can do. And on top of it, if you look at failure, you don't have to postulate any failure mechanism. It will come out automatically from your analysis, which is quite a good feature, I would say. Now, a colleague of mine always said there's no such thing like a free lunch. Okay, so if you get invited for lunch, then the guy wants something from you. And that's the same thing here. There's nothing for free, okay? You have a few disadvantages. So, for example, and that may look strange for you at the moment, but the domain to be analyzed is in geotechnical engineering not so clear. If you have a structure, if you have a bridge, you have the bridge, you have the geometry, the material, you have everything. But in geotechnics, if you have a deep excavation, a tunnel, how large is the influence zone of your structure? It's not always that cut clear. Again, you have to be careful when you do a drained analysis, an undrained seepage dynamic. This also poses challenges on your domain you have. Initial stresses, sometimes difficult to assess. So we have to interact with the geologists and with experience with the rock mechanics guy to see, at least to get a rough estimate of Keynote, the initial stresses, OCR, etc. There are always some uncertainties in ground profile and groundwater conditions, even if you have a perfect site investigation. I assume that you in South Africa also don't have a perfect site investigation, as we don't have in Europe. You always miss something. And that is there, but we can live with that, I would say. We have simplifications in modeling of the construction sequence. I mentioned that already. And more importantly, in ground engineering installation techniques, we are still struggling in modeling construction of stone columns, etc., mixed in place, and so on. People are doing this in research, but it will take some time before that comes into practice. So although the solutions are approximate solutions, that is always one we have to keep in mind, all numerical solutions are not exact solutions. But that's no problem, because we don't know the exact solution anyway. Because if we have a deep excavation here in Durban, who knows the exact solution? And actually, we don't care. So we have to have a good solution. It will be approximate. And that's why I think the pros beat really the cons. Now, just to make clear, I'm concentrating here on the finite element method. But of course, you can find a different method for people who use FLAC. To some extent, boundary element method, and also we have this continuum-based methods like the discrete element methods. They use it quite a lot in rock mechanics, but you can also use it, for example, in investigating soil behavior at a small scale, like investigating detailed grain-to-grain contacts, etc., in laboratory testing. But I'm concentrating here on the finite element method. Now, just to show you the development we had within 35 years, this was finite elements in geotechnical engineering 35 years ago. It's part of my thesis, actually. You see, we had 20 elements, 25 elements. And for these elements, for these meshes, we had to send it overnight to the computer center in Manchester. You won't believe it. Today, if Rock Science or Praxis or any other code would have an Android version, you would actually solve it in the coffee break on your mobile phone. So that is what we had. Few elements, very simple constitutive models, no user-friendly codes. I remember the students, when we start doing this, after 6 weeks, they probably got the first results because they had to fiddle around with the mesh and everything. Now we have this, now this is different. So this was really for freaks only, okay? I think you call it NURBS these days. But now finite elements today, and I just shown a few examples, while you have several 100,000 elements or more, 1 million elements, you solve it on the desktop, no problem. You have, I say, reasonably advanced constitutive models. There's still some work to do, in particular for dynamic loading and offshore and things. Things are not yet solved. There's a number of codes available, Praxis, TED soil, rock soil, FLAC, you name it. So they're all there, and they are very user-friendly. You can do the 3D analysis on the desktop. Now, I said the last sentence here is everybody can do it, but not everybody understands it. So when we give courses for practical engineers, sometimes we realize that they, in particular the young guys, they are very nice in handling the code, but not always understand what they're doing. And that is what is important. It is only a tool. Finite elements won't solve any problem for you. It's just a tool to solve it. Now, to sum up this, the goal of modeling is to understand, and that's what I put on the first line here, understand the behavior of geotechnical structures. So don't be too picky on the numbers in the first place. Try to understand the complex behavior of your system. But of course, at the end, we want to have numbers for design, so we want to have calculate the displacements under working load conditions. We want to have internal forces for design, and we want to identify possible failure mechanism. Now, I think we can achieve this, but we need appropriate geotechnical models in the first place. So that is what I want to emphasize here. Before you go into the computer, you have to really consolidate all your knowledge you can gain wherever it comes from to make an appropriate geotechnical model, because there already you do some simplifications. You will never be able to model your soil profile or your situation in a perfect way. And then this is again in red. You need a very good understanding of soil mechanics. Some people think, oh, okay, I buy one of these codes, that's fine, and I'm get rid of all the soil mechanics. But no, it's not. You need a proper understanding of soil mechanics because you need to know how you transfer soil mechanics principles into computational geotechnics. And you have to understand to some extent what the software does, in particular the constitutive model. You don't have to be an expert in solving equation systems of 1 million unknowns. That's done. That the codes will do automatically, but you have to understand some principles how the code works. And you need a clear picture of what you can do and what you cannot do. Again, I put it in red here. We do models. We do not do reality. Okay? We try to put reality as close as possible into our model, but it will never be perfect. So that is fine. So this is an example here, I think, from an excavation with a deep foundation in Bucharest. If you look at the site, it doesn't look like this on the computer. And here for the big cavern we did for a power station, it's all inside the rock. And this one we did a couple of years ago. It took about 10 days to run because the client wanted to have all these edits and things into the model, and we had about 180 construction phases to model. So that was it. Now, just a few on the on the constitutive models. Many people still think we can get away with more Coulomb. Now, more Coulomb, strictly speaking, is not a constitutive model. It is a failure criterion, and as such is not too bad. For drained conditions, not too bad. We have extensions which are slightly more accurate, but is okay. And you see here, I put one thing in red. This is the elastic modulus. That's why people like more Coulomb, because it's only 5 parameters. But I can tell you this E does not exist. For a soil, we do not have such a thing like an elastic modulus. Except maybe, I come back to that in a minute, for very, very, very small strains at dynamic loading. But that number does not exist. And now I'm questioning you a bit. So the last line here, if you do a geotechnical report, how many of you define the dilatancy angle? Hands up. I think it's about 0. But I can assure it's the same thing in Europe. Okay. But once you do your analysis, you have at least to think about it. Don't take what the codes do as a default value automatically. Okay? Now we're doing better now. If you just want to go for failure, more Coulomb may be fine. Again, only in drained conditions, not so in undrained, in particular for normally consolidated soils. But we can move on, and the next step would be using one of these critical state-based models like a modified chem-clay model. Again, you have a clear set of parameters doing much better than more Coulomb because it will fit the constitutive behavior below failure in a much better way. Again, there are, I would say, hundreds modification of the modified chem-clay model. And if you go today on a conference on numerical models, you will still find a couple of people, again, twisting on one of the parameters to make it a bit better. Then we have this class of elastic plastic double hardening model. Here you can get the parameters reasonably from standard tests, or there are some correlations, or is a lot of information available how you can get the parameters if you don't have all the tests. Again, every commercial code has a similar code, a similar model now, like this one was originally from Praxis, but most codes have a very similar model these days. It doesn't matter which one you take. I usually prefer to talk in class of models and not in a particular model because, you know, they differ in some details, but at the end, they're doing similar things. That was, I mentioned before, small strain stiffness. So we know that the behavior of a soil is elastic at very, very, very small strains. And usually we take this into account. This is important. Again, all commercial codes have this now. And we need that because we need larger meshes, or we need a mesh where we say the boundary should not influence the results significantly, but that means far away from the action, so to speak. We would have very, very small strains, and then if we have very small strains, we have a high stiffness. And that means if we get the wrong stiffness there, it will influence the whole behavior. Now, something which I do not understand, why it is not more popular, is to take into account structure. I will show it in the CPT example later on. This has been, this is clear that most clays in situ have a structure, and you can model that relatively easily by just introducing a second yield surface on top of the intrinsic yield surface. So as I promised, I'm not going into much detail of the constitutive modeling. Now, not yet standard in commercial codes are kinematic hardening models, modeling dealing with anisotropy, hyperplasticity, etc. There's a lot more available already, but which has not been really transferred to commercial codes. But you see here a website on there where you can download UMAT for Abacus and for Plaxis, where you can download models and use them if you need this. So I would say for standard problems like tunnels, deep excavation, basically the constitutive model issue is more or less solved, I would say. Well, there are some details, but once you go into cyclic loading, offshore, and these sort of things, you have to be careful, and there's still a lot of development going on. Okay, now parameter determination. That's an issue which sometimes prevents the application of numerical models in practice because people say, well, I don't get the parameters. Now, first thing, there is no universal soil model. So if any researcher or company wants to sell you this is the model for soils, forget it. It's not true. We have models which work better for soils, which work better for clays. We have models who work for both reasonably well, but this is no universal soil model. The problem is sometimes that that similar parameters have different meanings and consequences in different models. And that is what I meant earlier on. You have to understand what your code does and what it does with your parameters with a particular model. And that is something which as practitioner you may not care too much, but strictly speaking, when we talk about material parameters in geotechnics, they are not always real material parameters. So let me give you a simple example. If you have a quartz sand, then the material is the same whether it's in a dense or in a loose state. But if you use a constitutive model, you will actually input a different stiffness for the loose one and for the dense sand. And so if at university you go to the mechanics department and tell them this, they say, what are you doing? These are not material parameters. This is a mixture of material and state the material is in. So that becomes a bit tricky. There are models around who can do that, but they are not that easy to handle. So I would say from a practical point of view, well, we are used to live with this sort of assumptions and simplifications, and there's nothing wrong as long as we realize our limitations. I think that's one important thing as well, that if you realize and you're aware of your limitations, it's fine. You will do the right thing. In situ testing, I come back to that in a minute, the problem we have in laboratory testing is, of course, that we have sample disturbance, and I know, for example, a typical soil we have in Austria, odometer from this, I have to multiply it by 3 for the finite element solution, because otherwise the client says, well, if that's correct, I cannot build it. And we know it's not true, because we know that the soil is very difficult to sample, so that we need that we need some adjustment on that. So I'm a little bit more in favor actually of the in situ testing, and I will show that later on. It's also not straightforward, but I think you can get something out of it. Now, this is an issue which also comes because usually when you do the site investigation, you don't know what tool you will use for the design, so you cannot really steer the site investigation to get you the parameters you need for the model. That's what it is. Okay, and of course we know whatever we do, our parameters will scatter within a certain range. There's nothing we can do about it. So this objective parameter determination for advanced model is actually not a trivial task. But a couple of people are working on it now, and at the very end of my presentation I will come back to that. But first of all, I show you something which some young guys I experienced, they dream of. You go to Google Maps. Sorry, I put my hometown, not Durban. You say this is a site here. You click on the site, you get a profile of your layers. That's available in some places, so that's already there. But then you click on one soil layer, and then you choose model A, B, X, and then you choose model B, and then you get all the parameters. That would be the dream, wouldn't it? Okay, it's not like this. Okay? Now others think they can do it with the relative density. Actually, this guy Brinkrevit tried it a couple of times. I have to admit it was not that bad. He was using correlations. It was not that bad, but still, it is a bit tricky. And I like this. I like this report from Main and others. Is one number enough? I think that's really a question. You get a CPT, you get a SPD, you get one number, and then you build everything around it. I think it's not a trivial task. Now, people doing now machine learning, neural networks, etc., improves it, but I'm still a bit careful. Now, what one of the PhD students of my colleague is doing now, he's doing it with in situ testing, with input parameters from a CPT. So he gets a raw CPT data, plus, and that is something I would really encourage you to do, if you can do a CPT, if your ground conditions allow you to do a CPT, do a seismic CPT. Because then you get the shear wave velocity and you get the shear modulus at very small strains. And that is already a parameter from which you can build up the rest. So what he does he has programmed all the correlations he could find, and at the end, he wants to get the constitutive model parameters. Okay? Now what he does is, he called it an automatic parameter determination. So he used graph theory to get from one part to the other one. And of course, he has to do he has input some restrictions so that you don't use, let's say, a correlation which is valid only for clay. You don't use it for sand. So in the first step, he's doing a layering. You can choose at what thickness you choose the layer from the CPT, and then he picks up that. But still, at the end, he may have 5 correlations for this parameter, so which one you take. So it's still a bit tricky to do, but that's something he's working on. And the one thing is you can check how you arrive at the different parameter. So it's open, it's all open. So you can check and trace how it arrives at a certain parameter. There are other people working on similar tools on this automatic parameter determination. It will be a step forward, but I see that there's a little bit of work to do. Now, after this sort of introduction, I will show you now 4 examples. The first one is an anchor load test. And that was an anchor test only for research purposes, so it was not part of a construction. So what we did is we installed the actor vertical. Okay. And the nice thing here is that so it was a ground anchor, so we had a 12 meters of free length, 8 meters of fixed length, and 6 strands. Now, it was part of a PhD of Carla. She came from Brazil, and you see here the snow. On your birthday, she had to accompany this test, so she remembers that for a while, I think. Okay, so what we did is, we had some site investigation because it was near to a railway line construction, so we had a bit of site investigation. We did had a CPT, we had a seismic CPT, and that means from the G0 we could work our way through G and GUR and EUR. For those of you who are familiar with this type, so we were using the Praxis hardening soil model here. Now, so we did it because it was vertical, we could do it with an axis-symmetric model. We increased the K0 along the fixed length due to the grouting of the bonded length. We increased the K0 to 1. That's something we usually do. We have prescribed displacements at the top of the fixed length, so we didn't model the full free length, of course. Now, what we did with the grout, we modeled that with a model for concrete, which was developed originally for shotcrete. So it can take into account the evolvement of stiffness and strength with time, but we switched that off here because one of the features we had input into this model was that it could crack. Okay, so we had the peak strength, and after the peak, you would have a decay of the tensile strength roughly to 0. Okay, because we wanted to see the development of the cracks in the bonded length. And you need to remember this parameter HT. So the HT, if it's less than 0, it's still without cracking. If HT is beyond 0, between 0 and 1, it is cracking, and if HT is at 1, then it is at failure. So these were the parameters. I think I'm not going into much detail of that. Now, you would say, well, there's nothing new. I mean, we do the fiber optic sensing, that's quite common now, and I think it's a game changer in monitoring. But what we did here, we did apply the fiber optic sensors on the tendon, but also in the grout. And I think that was pretty new, because on the tendon, some other people did it, but we wanted to check what happens in the grout as well, so in the fixed length. So that's a bit of work on the site, of course, because it's quite tedious to apply all this, but we did this in cooperation with Keller. The results I'm showing in the next slides are along the fixed length, more or less. Okay, and the displacements are analyzed at the top of the fixed length. Now, this is the displacement and load curve we got, and you see that the red lines or the dotted lines is in situ, and the black one is numerical. And you see here, I pointed out it was a class A prediction. Okay, so we got some information on the site, and we did the analysis before the test. And when I saw this, I said, well, I can retire because it won't get any better. So I did a couple of years later, but so what we did not take into account is this creep measure. You know, when you do the load test, I guess you do a similar thing here. After a certain time, you have 2 millimeters of creep and say, well, this is failure. Okay, we didn't take that into account. That's why it is a little bit stiffer. But at the end, I think we did reasonably well. But the nice thing what you get out from this from these measurements is, so you see here the full anchor, so the free length, of course, the strength, but then you see, so from left to right, it's increasing load. And you see then that how much of your bonded length is activated at a certain load. And you see at the end, when it failure, the whole bonded length was activated. Okay, that's what you expect. You would not, of course, you would not design it for that, but in this particular, where it was only the test, we could do it to the far end. So that is very, very nice. Now, if we compare again at two different load stages, if we compare the analysis and the numerical analysis, the in situ measurement and the numerical analysis, you will see that we have quite a good correlation between the two. Now, this zigzag is because at some stage, we experienced the cracks. Now, the model, I forgot to say that, the model we do is what the structural engineer call a smeared crack approach. We cannot follow how the crack develops. We can just say, well, this stress point has cracked. Okay, so that I have to say is a limitation. Now you see here these oscillations in the measurements. They are indicating cracks, and that is what you see in the analysis. And you see I plot the HT factor here. That is what I mentioned before. And you see at the higher levels you get a very high number for the HT. That means you are fully cracked. So that is what gives us some sort of idea how these anchors behave. So I just show a bit of it. That is what you see on site. It's quite impressive. So you see on the left-hand side there were two sensors on the left-hand side and on the right-hand side, and in the small picture here you see the applied load and unloading reload. So that is what you see on site. So you see the cracks coming in at some stage, etc., and how much you mobilize from your bonded length. Now, in order to get the numbers right, you need quite a bit of post-processing. Okay, so but on site you can already get a feeling what is happening. So I'm not playing the full picture because it goes on for 2 or 3 minutes, but that's just an indication what you already see on site. Now, in this research project, which I'm not going to elaborate further on, we did this in different conditions. So we had this clay silt, then we had a gravel, and we also did it in rock. And I just show the comparison between the Seeton, it's the German word for ton is clay, but it's not a clay, it's a clay silt. Okay? So we had about 1,500 kilonewtons, and then we had fully mobilized the bonded length. But if you do the same thing in rock, and that was an anchor for a real construction site. So we just took one anchor and took it. So it took only 3 meters for getting in the load in. Now, usually you would associate that with strength, but it's not entirely true. And I think that is something I want to raise here. I think in geotechnical engineering, we often don't think enough about stiffness or relative stiffness, between, let's say, a support and the soil. And this again here is the case, because there's a lot of this, how far it goes, is influenced by stiffness and not only by strength. And that is something I think we should work on more. And of course, it's advocating numerics again, because we can at least vary stiffness, whereas in conventional design, you often ignore it. So that is something which is nice. Now, if I have a question to you, how long do you design for the bonded length? 6 meters? Okay, not bad. So this guy here was using 10. I don't know why. Okay, but you know, you could use these measurements actually. If you do it on site, you could actually see really what's going on site measurements. Now, second example, slow-moving landslide. These issues we have sometimes. So there's a reservoir here from a pumping station. There's a slow-moving landslide. Of course, we measure. It's quite 270, 220 meters. Movement rate roughly 40 to 50 millimeters a year. And the water level changes up to 7 meters. Okay, it's one of these stations where you pump the water back and then you have the water level rise. Now, of course, they don't like to move the slide into the reservoir. That is not what is expected. So you, of course, you put inclinometers, pore pressure measurements, etc. So that is at the basin itself. We had a similar soil as we discussed in the anchor. It was a fine sand, silty clay, etc. We had pore pressure measurements there, and we had inclinometer measurements as well. So sometimes in these clay silts, we have very fine layers of sand, which makes it quite difficult to judge whether we should undrained or not, because you will consolidate a bit during construction. So that is. So we had a competent rock there, then the sheared rock in the transition zone, and the sliding mass. So we had some measurements. And what we figured out when we measured that we had excess pore water pressures in the subsoil, depending on the water level velocity. Now, what I mean with excess pore water pressure is you see the black line here is the water level, and these ones will be the static water pressure. But when we measure it, when you change the water level, you not straight away get the static water pressure. Now, there are several reasons for that. Sometimes we think that the sediments in this basin are probably not yet fully consolidated, so you will have still some pore pressures, but also you will have, you may have air bubbles in the soil, in the water, sorry. And then, of course, once you have air bubbles in the water becomes compressible, and then you have a delay in when the pore pressure develops. So it makes a bit of a change how fast and how high you change your water level. Now, when we look at the at the inclinometers, you could see that when they increased the water level, they have an increasing in displacement rate, but the precipitation, rain, etc., did not make that much of a difference in this inclinometer position at the toe of the slope. So what we tried to do, well, I come back to this one first. So that is what some people call a quasi-saturated soil. So it does not have a continuous air phase that we will usually deal with when we have an unsaturated soil, but we have a quasi-saturated soil with some air bubbles in it, but that means you have a compressibility, and you can take this into account these days in the numerical models. Then we were asking ourselves, well, is there some creep in these lacustrine sediments, which we could expect? So we used the soft soil creep model for that. Well, there's nothing special on this one. We had some data, CU triaxial test, odometer tests, and we came up with a reasonable set, what we hope with a reasonable set of parameters. Then we then built the model. And what we did is we built it up. First of all, we had for the transition zone, we had, of course, to find out or estimate the degree of saturation, and then assume something for the relative permeability, etc., because we wanted to model the whole slope then and see what influence different issues have on the deformations of the slope. So what we did, we started with the intact rock, then reactivation of the sediments, did some consolidation on the sediments, then we were activating the sliding mass, and then we had a creep phase, so 4 years, and rainfall and water level changes for about 1 year. Now, of course, we had some data on rainfall, snow, etc. But what we did is we made this very simple. Let's say, so we modeled the total precipitation roughly then as an average precipitation, evaporation based on literature. And what we did when we had snow covering in the months where we had snow covering, we said, well, we have no or very little infiltration in the months when the snow was melting. We had then a bit more. Of course, you may argue we have to make a lot of assumptions here. That's correct. But at the end, I think we managed to do reasonable. We had measurements on displacements on the slope. And the goal was now, and that is nice, I think, with numerical methods, because if you need measurements, you need monitoring, but when you look at the monitoring results, you cannot really distinguish where it comes from. Did it come from the creep? Did it come from the rainfall? Because you just have the measurement. That's it. But the nice thing when you do this numerical stuff, you can say, well, I switch off this, switch off this, switch off this, and see what is the contribution of each of the factors. And so we looked at creep, dissipation, precipitation, and the water level changes. And what you would probably guess is that these 4 factors are not equally important for all the points. It will depend on the location. And that is what we did. So you see here, this is measuring point E. And you see here, that's the measurement, the knot. These ones are the measurements. The green one is is the end of what we predicted. But we then splitted it up. The creep part was that. The dissipation part is this. The precipitation is this. And the water level changes is this. And then we did it for the 3 nodes, and you see now that it's different. So the creep is more important than the lower part because there is the sediment, and the precipitation is more important on the upper part. So we have node E, node F, and the water level changes that are roughly more or less the same. So I think that is something you could explore. You know, you can play around. I know in practice, time is money, and you have the client is waiting for the result. But still, you know, you can do these things maybe overnight, just change one thing. That is what we always do. If the client pays us for 3 analyses, we do at least 6. You know, some of them we just change overnight and see in the morning, is this roughly the same or is something different? Because we had a couple of cases where when you change one parameter a bit, you get a completely different result. And then you have to warn the client and say, see, if I change that a bit, are you sure that it is this value? Because if you change it a bit, the behavior may change. These things happen, you know? Okay. Well, that was in point D. That's the same thing in point F and G as well. So I think we did quite reasonable on that, and we gave them some hints how they should do the water level changes, if possible. Because sometimes, you know, but at least they are aware of that. If they're doing it this way, it will be less favorable as if they would do it the other way. Now, final word on this one. What's a factor of safety? Peter is laughing. What's a factor of safety of a moving slope? I think we probably can spend the whole day just discussing this. Some people say, well, it's failing. Some people say it's roughly 1. Well, I think this factor of safety business is something we invented. The engineers invented to work with it, but it's a difficult story. Okay, so and sometimes. Probably you have the weird situation here as well. Sometimes the authorities, they think, well, if you do some cut, or like in this case, you do something and the soil is moving, you have to do some measures to support the slope, and you have to reach 1.25. But the slope was, at the beginning, was at if you calculate it, 1.03 or something. To bring that back to 1.25, because unfortunately, it's sometimes not possible because the mass is just too large. Okay? So what we sometimes say is that if you do something to it, you have to provide the support measures in such a way that you don't make things worse. Okay? And here again, we checked a bit what the factor of safety is, and you see you're talking about percent. It's very close. It's very difficult to assess that with numbers you would find in the standards. So we also checked the inclinometers, and we got that also quite reasonably right. Now, next example, that's my hobby at the moment. I have still a PhD working on that, is cone penetration test modeling. Now, forget about any standard code. It won't work because you have large displacements, large strains, your elements will distort, and the code will blow up immediately. Some people do it with a trick. They make a small gap in front of the cone and remove that, so I don't like that. So what we are using here is what we call the particle finite element method, developed in Barcelona, UPC and Chimney. So what we do here is a fully coupled analysis. Saturated here, we can do only saturation in this case, and in this presentation I'm only showing the undrained condition. So what we do is we continuously remesh. Okay, so that is for the numerical guys amongst you. It's an updated Lagrangian formulation. You make a new mesh every time. Well, you have some measures when you do the new mesh, and you transfer state variables and information from one mesh to the other. That's not a trivial thing. That's why it took quite some time before these methods became available. There are other methods around MPM and so on which can do similar things, but that's not trivial how to do that. Now what we use here is very simple elements, because the meshing becomes tedious if you have very high order elements. So we use very simple 3-noded elements, but they log. That means they don't give nice results in undrained conditions. So that is what is called here stabilized mixed formulation. So we have, for those of you, we have the Jacobian as an unknown as well in the formulation. We do a frictional contact between the cone and the body. And as a soil model here, we use the clay and sand model, including destructuration, and that's a point I want to make here. So the clay and sand model from you is basically a modified chem-clay model, but you have additional parameters so you can distort the modified chem-clay ellipse a bit, and then you get different undrained shear strengths, etc. It's a reasonable model, I would say. It has a state parameter. That means it checks the state at a given mean effective stress, the distance to the critical state line. And that is what we added to the code. We can do it now with the structure. Now, as I said before, this is available 93, so that's quite a long time, 30 years. Jens and Nova presented the work how you deal with structured clays in a constitutive model. It's pretty straightforward, and is still used by many people using structured soil. So basically what it means, if you have an odometer, at a given void ratio you can sustain a higher vertical stress than without the structure. But once you destroy the structure, you see here, you will you will come down to what we call the intrinsic normal consolidation line. So that is what we put in, because we wanted to check what happens during penetration with the structure. And this DH here, this DH parameter, means how fast, well, in easy terms, how fast the structure decays. Okay? And of course, it has a volumetric term and a deviatoric term. So a volumetric and a shear term. Now, splitting the two is not that easy. There are few papers around, but not that many, because it's not so easy to determine experimentally what is what. Okay? So we had to play around a bit, but when you see now on the right-hand side is the B0 here is the amount of structure. Okay? It's a number which just tells us how larger the yield surface is compared to the intrinsic one. Okay? And the H is the rate of decaying of structure. And now some people will say, well, why do you bother about it? When you do a CPT, you will destroy the structure straight away. You don't have to bother about it. I argue it's not the case. Because, first of all, you see now here, these parameter here, at the vicinity of the cone. Now, of course, if you have a high destructuration, H is 10, you will destroy the structure in a wider area near the cone. If it is not very sharply decaying, then it will have only a small area here. Now, when you look at the tip resistance, it is not only influenced by the vicinity of the tip. You know, you need a larger bulb which is reflecting the tip resistance. So I think it is important to take this into account. And you see in the next slide what happens. Now, what we checked is once you pass the tip, you get a stress state near the tip, on the side of the tip, which is roughly triaxial compression. So that was one of the first tasks the student did, which was actually not that trivial, because when you refine the mesh all the time, it's difficult to have a fixed point to compare. So what he did as first task, he introduced fixed points where the remeshing always had to have a node, so that we can look at the results on this one. And by doing that, we figured out that we have roughly intraxial compression. So these are different degrees of structure. You see 0.5, 50, you get different under-end shear strength. So what we did now, we ran the CPT with different structure and looked at the results. And because we did the same thing with the same parameters, we did the triaxial undrained test first. So we said this is our SU, so we did it the other way around. So we tried to work out the NKT. Usually, you guess the NKT, and then you know the SU. But we said we know the SU, and we get the NKT. And now you see with the different structure, you get, of course, different QT, but the NKT doesn't change that much, because so the increase of the structure is reflected in the increase of the QT. So that means if you don't manage to get an undisturbed sample into the lab, so you know the intrinsic value, you run the CPT with the intrinsic values, and it doesn't match the QT, you can estimate upon the structure. Sounds a bit difficult, but actually at the end is not that bad, and you can make this automatic, because the CPT cone is always the same. So that's what it is. So you can make this very automatic, and actually coming back to the slide I had on the parameter determination, what we're doing now, that we combine the two students. So the one who does the automatic parameter determination, he gets in the CPT, the raw data, provides my numerical friend the input data, he runs the CPT, and then he comes back to him and says, no, or yes. Actually, it worked better. We had one round going already. it worked better than it looked like. So I think that would be a step forward again to do it. Now this is from I have to speed up a bit. That is from a real site now. Again, these are the parameters. We got a shear wave velocity, some odometer test now from a block sample. So we got a reasonable quality of the sample. We estimated the parameters then from the odometer. And that is the result. You see the gray one? This is QD over FS. This is the result in situ. This is our numerical result. And if we would ignore the structure, we would end up here. So I think it shows it works. We do the same thing with the pore pressure here. By the way, the U2 position, I think that's not the best position to measure pore pressure. Numerically, you see it. You get much more consistent result in U1 than in U2 because you have the corner and it's not doing like this. Okay, but that's what it is. Okay. Final example. It's a failure. And that is something, well, I put in here because I want to challenge you a bit. You do slope stability, you do with limit equilibrium, correct? It's okay. But sometimes it may not be okay. And I'm showing this example. So it was a failure of, I probably show the cross-section here. There was a natural slope, pretty steep. We have the slopes in the Alps, 40 degrees, and so roughly, approximately stable. What they did, they wanted to build a road on top of in here, so they did a reinforced embankment there. So the failure was not in the reinforced embankment, that was fine. They had a sort of abutment here at the end, which they didn't anchor back. Don't ask me why, but they didn't do it. Because in a similar occasion, they did. Okay. Well, that failed. And the guy who was doing the design, he said, well, my factor of safety is 1.3 or whatever, everything done correctly. And then the authorities said, well, could you probably check with finite elements whether you find some different result? So we did that. Built that, so we gave it a hook, so we made it sure that there's no failure in the embankment. Now, the strength parameters given by the geotechnical report were 40 degrees, a friction angle, and 0 cohesion. Now, I know the guy who did the geotechnical report. He's not the brave guy. That was conservative. He was still thinking there's some, well, it's cohesion, I don't know, but it will be some interlocking of particles, etc. But he gave that as a design parameter. So when we back analyzed the failure, we ended up with 40. We left the 40 degrees, but it still had to have a cohesion with 11. Even with a cohesion of 11, it would fail. Okay, so that means the FS of the natural slope was about 1.25, and that is where it failed. It had about 1 or 0.98. So it failed before they reached the top and before they applied the variable load. Okay? And this took, well, my students, they are really fast on doing that. So this took maybe an afternoon, not less. Okay? We just found out straight away, did everything we got, it was failure. Okay? And the reason is simply, you see here the failure mechanism we got. We did this again with what we call failure. That's finite element limit analysis. It has been pioneered by the late Professor Scott Sloan in Newcastle and his group. That's basically finite elements with rigid elements. You cannot do deformations, but it's based on the theory of plasticity, upper and lower bounds. It gives you quite good solutions. So we compared that with finite elements, and what I want to draw your attention here is you get 1.21 when you assume the dilatancy being equal to friction. For the numerical guys, associated flow rule. You never ever do that with more Coulomb. But we found out in many cases that with limit equilibrium, you inherently get this result. Whereas in limit equilibrium, the latency angle does never come up. Now, if you do it, let's say, with more sensible parameters, you see that whatever you do, failures, finite element limit analysis, you will end up in getting failure. And at the end then, okay, we put in some more anchors and we played on the safe side now here. So I was not, because we still had the discussion with the guy who was designing originally, that wow, it was all right, and it was a bit of thing. I said, well, I'm not signing if you don't do these anchors in here because we don't do any further risk. Okay, so I'm a little bit over time, but there's still couple of more slides. Well, a summary of the results. So I think this fiber optic sensing, that is something I like. It's really good. Now for the anchors, you could actually apply the sensor at the manufacturing stage. You don't have to do it on site, on the tendon, not in the grout. But I think the grout that was for research, you don't need that from a practical point of view. It was just to look at it, what happens in it. And the nice thing is, remember, well, think about you have a wall with 200 anchors, and you want to check them after 15 years or so, the one on top of it. You have to close the road, find out how to go there. Now, if you have a fiber optic sensor, if you have a long enough sensor, you keep it somewhere, save it, and you just have to come with the equipment to measure. It works. So the people do it now. So that's a bit of a game changer, I think, in monitoring. I like that. And actually, Kenichi Soga, in his ranking lecture, the recent one, he showed that as well. He had very impressive examples. Okay, then, okay, for this landslides, again, we can check the different contributing factors. So it's more powerful than doing a standard analysis. Penetration test, I think we can use that in interpreting CPT a bit better and other penetration methods. And for the slope, limit equilibrium methods are not always conservative. I'm not saying we should get rid of them. That would be a bit too much, I think. But we should think of alternative methods. And for example, if you have your model already for working load conditions, why not use it for failure as well? Of course, you have to be a bit careful with all the tolerances and convergence criteria if you really go to failure in finite elements. That's correct. Some people argue about that. But if you do it properly and you have an understanding, you would be able to do it. So I think we should rethink a bit. We cannot say, well, we have done this for 30 years and that's fine. Yeah, it's fine. I'm not saying this is wrong, but I think we can move a little bit forward. We also need experience with these methods. That's for sure. You cannot switch from one day of the other to a complete other method. But then we probably also have to rethink factors, etc., etc. Okay, stiffness coming in, this sort of thing. So that is what I think. Now, final remarks. I borrowed this from Gino Vigiani. He says geotechnical engineering is complex. I tell to my students it's interesting. So don't do structural engineering. Sorry for the structural guys here. This is boring. You know, it's concrete. You know the material. You know everything. Geotechnics is interesting. You know, you don't know anything. I usually say, student, the only thing we know exactly is the gamma of the water. The rest is uncertain. And I think, but that is challenging, and that is good. And it's not because you buy a finite element code or flag finite differences that it becomes easier. No, it becomes more difficult because you have to understand this. But you gain, hopefully have shown you that a little bit more out of there. And then don't blame the code if it goes wrong. You know, any code, first 5 pages, disclaimer. You are responsible. So even if the code does something wrong, you have to check and make sure that you do it. So you need a nice tool, but also you need a good understanding. And this is, doing finite elements is not design, it's part of it. Okay? So I call it, it's a powerful tool, and I call it computer-aided geotechnical engineering, but it should not be like a cage. You know, you should not be confined to it. You should interact with all the other people doing that. Okay, that's almost my last slide. I have a few references selected. But at the end, I promised I make a short remark on what everybody's doing now. Machine learning, neural networks, artificial intelligence, all this. I'm not at all against it. But we have to be a bit careful. We should use the possibilities these tools offer. We should make use of it. But I found a nice cartoon in one of our local newspapers some time ago. And there you see this robot, artificial intelligence, on the couch of Sigmund Freud. And the psychologist said, what is your problem? And he said, I'm afraid they expect too much from me. So I think that's a bit, many people think, that will solve everything. It will help us to solve, but it will solve nothing. And I think for a couple of years, natural intelligence and experience will remain essential, because we have to check what these artificial guys are doing. And many times they probably will do better than we would do, but sometimes they will do worse. And I think it's still our responsibility to check that and make sure that we do the right decision. And on top of it, I think you cannot sue a computer, at least not yet. With that, I thank you again for inviting me, and I thank you very much for your attention.
Thank you very much, Helmut. My PhD professor always used to say, fools with tools are still fools. And I think I think this is very, very, very similar. So the only thing that I took from there is one lecture enough, probably similar to one parameter is enough, and I don't know whether one lecture is enough. There's probably so much more still to say. But I do thank you for coming out, enjoying the country, presenting the lecture. It was a wonderful insight that we are, in many aspects, on the precipice of numerical modeling. I think we've come a long way in many aspects, but we are still far off on other aspects. So thank you very much.
Okay, thank you for inviting me. It was a pleasure to be here. Okay.
Just a short.
Okay, thank you very much. Thank you very much. Thank you very much.
Thank you.